अरे बैटरी खत्म हो गई MP1 में। हाँ जरा एक मिनट आ जाओगे फटाफट। Okay, so let me start the last topic of this theoretical computer science. And वो बंद कर दो दरवाजा, ठीक है? क्लोज द डोर। डिस्टर्बेंस हो रहा है, राइट? Okay, so I have to talk about. So I talked about finite state automata, push-down automata, linear bounded automata, and Turing machine. And now I am going to talk about universal Turing machine, and that will give you an idea. In fact, my job is to show you that there are certain problems which Turing machine cannot solve. In other words, I will show you that there are more languages than the number of Turing machines. So certainly, there will be problems which Turing machine will not be able to solve. In order to do that, I will use a technique from from mathematics, known as countable, uncountable. I think in calculus you might have seen this countable, uncountable. Have you seen this? Very good, very good. So it's kind of incomplete education anyway. So I will talk about it. That's why I'll briefly talk about that also, and I'll show you this connection. So So again, thanks to Professor Bush for these slides. And this is the last slide. I think there are total 10 slides which you need to look at before exam. But not everything in the slide. So I have skipped few things you can skip if you want. But if you are over enthusiastic, you can certainly look into those things. Okay. So a limitation of Turing machine is Turing machines are hand wired. They execute only one program. So real computers are reprogrammable. The solution is universal Turing machine. And what are the attributes? Reprogrammable machine and simulates any other Turing machine. So how do we simulate one Turing machine on another Turing machine? In that, if you want to do that, so we need to map each and every action of Turing machine and the content of the Turing machine into another Turing machine. Okay. So input of a universal Turing machine, description of transitions of machine M, and input string of M. So basically, universal Turing machine consisting of 3 tapes. One tape consisting of description of the machine. Okay. Second tape consists of the tape contents of the machine, and third states of the machine. What are the states? Q1, Q2, Q3, and so on. So key idea is we describe a Turing machine M as a string of symbols. Okay. So we encode M as a string of symbols. How do we do that? It's very easy. First, we look at the alphabet encoding. So suppose there are alphabet A, B, C, D, and so on. Say suppose there are all 26 alphabets of the English, right? So what we can do, A will be 1 because we need to use unary encoding, right? A is 1, B is 1, 1, C is 1, 1, 1, D is 1, 1, 1, 1, and so on, right? So unary encoding. There could be 10 alphabets, 100 alphabet, doesn't matter, You can just do this unary encoding, okay? Encoding of the alphabet. So each alphabet member is mapped into a string of ones. Okay. Very good. That is alphabet encoding. Second, state encoding. So there machine could have bunch of states Q1, Q2, Q3, Q4, and so on. Right. So each state again we map is like first state is 1, second state is 1, 1, third state is 1, 1, 1, fourth state is 1, 1, 1, 1. Right. Then we need to somehow map head movement, left or right. So if left move, encoding is 1, right move, encoding is 1, 1. So you can immediately notice that everything we are encoding as ones, right? So there should be somehow we should distinguish where the head is starting, where the state is starting, where the alphabet symbol, right? So we need some sort of separator in between, right? For that separator, we will use 0. So for example, is this transition encoding, the state is Q1 is 1 separator 0. Next, alphabet symbol A, which is 1. Okay. Next state 1 1. Again separator. Again separator. Another state, alphabet symbol 1 1. And then movement of the head, so which is 1. Left is 1. Right is 1 1. And so separator 0 is used in between everything. Okay. So using this technique, we can map transitions into a string of 0 and 1. Okay, a string of 0 and 1. So whole Turing machine encoding. So whole Turing machine encoding can be done. क्या हुआ? बंद करो ना, क्यों खोल रहे हो? नहीं तो उसके बंद करो, जाने दो ना उन लोगों को. Why they are coming now? Close it now. So Turing machine encoding. We have transitions. So one transition, full encoding is here 1 0 1 0 1 1 0 1 1 0 1, and another transition. So we need to separate these two. So remember, for alphabet, state, and head movement, 0 separator is used. Here, in order to separate two transitions, I am using 2 zeros as a separator. So now we have everything is clear, right? Everything can be converted into a binary string of 0 and 1. So basically, tape 1 contents of universal Turing machine, binary encoding of the simulated machine. So that is a tape 1 of the universal Turing machine has 3 tapes. Remember? So 3 tapes. The first tape consisting of binary encoding of the simulated machine. So like that, we have encoded the whole machine and the binary string on tape 1. Right? So basically, the idea is a Turing machine is described with a binary strings of 0 and 1, right? Given a Turing machine, I can describe it with a string of 0 and 1, right? Each Turing machine corresponds to a binary string of 0 and 1. Okay. Therefore, the set of Turing machine forms a language, right? The set of Turing machines forms a language. Each string of this language is the binary encoding of a Turing machine, right? Because each Turing machine can be mapped into a binary string, right? And the collection of binary strings is nothing but a language, right? So basically, the collection of Turing machines forms a language. Okay. So language of the Turing machine: one binary string Turing machine 1, another binary string Turing machine 2, another binary string Turing machine 3. All that collection is nothing but the language. Got it? Very simple idea. Now I need to show you about countable and countable business. This is kind of in between our. Now I want to show you that there are more languages than the number of Turing machines. The collection of Turing machines forms a language. Fine. Now I will show you there are more languages than the number of Turing machines possible. And that way we will say that there are certain problems which Turing machine will not be able to solve. Okay. So countable sets, I think it's very simple basic idea. In finite sets, when we talk, so if we talk about finite set, they are always countable. You can count, right? Finite number of elements. But if it is infinite, you may count them or you may not count them. And when we say we can count them, when we can really count them, we take one element, take another element, take another element. So basically what we are doing, we are mapping with natural numbers. First element, second element, third element, fourth element, fifth element, and so on. So we are assigning each element a natural number, right? So there is a correspondence with set of natural numbers. If we can do this correspondence, then we say that the set is countable. Right? Infinite set is countable if we can do this correspondence. If we cannot do this correspondence, then the set is uncountable. Okay, so I am going to give you examples of both. So countable set, if there is a one-to-one correspondence of elements of the set to the set of natural numbers, positive integers, right? Okay, so set of even integers, there are infinitely many even integers, but they are countable. How? So even integers are 0, 2, 4, 6. So I can say that 0 divided by, so this is the first one actually, this is second one, this is third one, this is fourth one, and so on, right? So this map exists, which is 1 to 1 and onto. If there is a map F from set of natural numbers to the set whatever which we want to count, if there exists a 1 to 1 and onto map, then we say that the corresponding set is countable. Okay, because we can establish a 1 to 1 correspondence with a set of natural numbers. So even numbers are countable. Fine. Set of rational numbers, are they countable? They are infinite. Set of rational numbers are countable. How? Because I can, if I say 1 by 1 as 1, 1 by 2 as 2, 1 by 3 as 3, do you think this looks like a approach, nice approach? No, because there are certain numbers which will be missed out of this. So what we can do, we'll never count numbers with denominator 2, right? Denominator 2. So better approach is we arrange everything. I'm only talking about right now positive ones. You can include 0 and negative ones as well. I'm just showing you how to it work for the positive rational numbers. So 1 by 1, 1 by 2, 1 by 3, 1 by 4, 2 by 1, 2 by 2, 2 by 3, 2 by 4, and so on, 3 by 1, 3 by 2, and so on, right? Now I can count like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Like this we can count. Now you can see that there is a correspondence with natural numbers. How? So 1 by 1, if you sum numerator and denominator, it is 2, right? It is known as height of the number. 1 by 2, the sum is 3, and 2 by 1 is also sum 3. This is 2, this is 3, then this will be 4, all this diagonal, then this will be 5. So basically there is a correspondence with natural numbers you can establish easily, right? Or in other words, we can count, right? 1, 2, 3, 4, 5, 6, 7, like that we can count. So if you want to include 0, I can place 0 up front. You start from 0 and then you count like this. So 0 will be included. If you want to include negative numbers, negative rational numbers, that you can insert in between negative numbers, right? And then again you can count in the same manner. So rational numbers are countable. Fine? Very good. By the way, as a T exercise, find a 1 to 1 and onto function f from natural numbers to set of rational numbers. This is a non-trivial problem. We have to find 1 to 1 and onto function f from set of natural numbers to set of rational numbers, right? There should be a 1 to 1 correspondence. I should give you explicit function. This is the function which is going to work, which will count for you. So set of rational number is countable because we are able to describe an enumeration procedure or enumerator for the correspondence of natural numbers. Similarly, let S be a set of strings language. An enumerator for S is a Turing machine that generates, prints on tape all the string of S one by one. So we just saw that collection of all Turing machine forms a language, right? It is an infinite set. And that set is countable. I mean, you can show that by this enumerator procedure. Enumerator for S is a Turing machine that generates, prints on tape all strings of S one by one. Okay, so this is our enumerator which is going to count that. Right. So for strings, this enumerator machine for S is output on the tape S1, S2, S3, right? Finite time. So this is enumerator machine, right? So basically, if for a set S there is an enumerator, then the set is countable. So the enumerator describes the correspondence of S to natural numbers, right? That kind of correspondence is there. So that means, our collection of Turing machine is countable. Okay, collection of Turing machine is countable. Okay. So set of all Turing machine is countable. Because any Turing machine can be encoded with binary strings of 0 and 1s, which you know. Find an enumerator procedure for the set of Turing machines. Generate the next binary string of 0 and 1 in proper order. Proper order means, we are actually looking at strings of length 0, strings of length 1, strings of length 2, strings of length 3, and so on. This is a proper order actually. By length, because length again correspond to natural numbers. Of course, there is, you can somehow correspond it to all natural numbers, right? So this length business will be helpful. So check if the string describes the Turing machine. If yes, print the string on that output tape. If no, ignore the string. Okay, so this is the collection of Turing machine is countable. Fine. Now uncountable sets. A set is uncountable if it is not countable. Okay, so this is the result. I'll give you a quick proof of this fact. This is very important. If S is an infinite countable set, then the power set of S is uncountable. Countable set का power set uncountable है. If there is an infinite countable set, look at the power set, that is uncountable. Okay, proof is very beautiful. You will observe that. So how do we prove it? Since S is countable, or set S is countable, so we can write elements as S1, S2, S3, elements of S. So basically every element of set S can be written as binary numbers, you see. So elements of the power set have this form: phi, S1, S3, S5, S7, S9, S10, and so on, right? So we can have a binary encoding. We encode each element of the power set with a binary strings of 0 and 1. This is possible, right? If set S has elements S1, S2, S3, S4, whatever, say S10 to S10, whatever, or in fact this is infinite, so it will keep on going. So it's a binary. So now, first element, if you take S1, 1, 0, 0, 0, 0. S1 is there, but rest of things are not there, right? Similarly, S2, S3, those things are 1, rest of things are 0. If the subset power set has S1, S3, S4, this is a binary encoding, right? So basically, each element of the power set can be mapped into a binary string. Okay, correct? So this is something very simple. Now, so every infinite, वो बंद कर दो दरवाजा. Every infinite binary string corresponds to an element of the power set. Similarly, if you take a binary string, I can say S1, S4, S5, S6. That is nothing but a element of the power set, right? So binary string corresponds to an element of a power set. Power set element is corresponds to an element in the as a binary string, right? There is a correspondence. Okay. Now the real proof. Let us assume for contradiction that the power set is countable. So you see, S is infinite and countable. I have to show that the power set is uncountable. S is countable but infinite. Power set is also infinite in that case, right? But this is uncountable. And so suppose it is countable. This is बहुत ही important है. ये थोड़ा सा 2 मिनट ध्यान देके देखोगे, so you will enjoy it. Suppose power set is countable. Countable means we can establish correspondence with set of natural numbers. Assume that we can do that. We can assume that the elements of the power set is countable. Okay, and so these are the power set elements, T1, T2, T3, T4, and we can have the binary encoding for them, right? We can do the binary encoding. Now, these are the elements of the power, power set T1, T2, T3, T3, and there is a binary encoding for them. Now, what I am going to do, I am going to produce a binary string T, which should be part of it, but actually it is not. It's kind of giving you contradiction. What I am doing, this binary string T consisting of, so I have write down, see, the set is, I'm assuming that the power set is countable. So T1, T2, T3, T4, there is a correspondence kind of thing. I have written there binary things, binary strings I have written. Now I am producing a string T, which is complement of the diagonal element here. The first element of T is 0, which is complement of 1. Second string is 0, which is complement here. This is 1, complement here. This is 0, complement here. So whatever comes in the diagonal of this, I am taking complement of that as an element of member of T, right? So T is a binary string like this. Understood? The production of T. Now, yes. So I am saying that power set is countable. I have assumed that the power set is countable. I have listed all the elements, right? Now I know that I have shown you that each element of the power set corresponds to a binary string, right? So all things written as a binary string. Now I am producing a binary string T, which is created like this. The first element here is the complement of the first diagonal element here. Produce a contradiction actually. I'll show you that our assumption is wrong. Okay, so this is 0, this is 1, this is 0, so this is 0, this is 0, this is 1, this is 1. Do you understand that? Everything is complement of the diagonal. Now this string T is also represents a power set element. It should be part of this, but the way it is constructed, it will never be a part of the set. You understand? Because at the diagonal entry, it will differ. Right? This is kind of a contradiction to our assumption that the power set is countable. Beautiful, right? It's a beautiful thing by Canter, Canter diagonalization argument. This is known as Canter diagonalization argument. Using the Canter diagonalization argument, one can show that element of the so the power set is uncountable. Okay, got it? So this binary string corresponds to element of a power set, but that will never happen. Then T must be equal to Ti for some I, but that ith bit T will not be equal to Ti, right? So there is a contradiction. So the power set of S is uncountable. So this is a beautiful result. If S is an infinite countable set, its power set is uncountable, right? So once you learn this fact, we can apply it to the languages. If alphabet is A comma B, set of all strings infinite and countable, so power set of this language will be uncountable, right? Power set of S contains all languages, which is uncountable. So now that means the collection of Turing machine forms a language. So its power set will be uncountable. That means there are more languages than the number of Turing machines, and hence there are problems which Turing machine cannot solve. Beautiful small fact. Done. So that's all about theoretical computer science, right? तो कुछ लोगों को नींद आ रही होगी, तो नहीं आ रही? So we can take the quiz, I guess. So do you have